Hello, dear students. Let us to continue the remaining part of this current electricity. So, in previous class, we have already discussed about resistance and resistivity, drift velocity, current density, and electric current and potential difference. Let us to discuss the relation between Vd, that is drift velocity, rho, that is resistivity, I, electric current, E, electric field, J, current density, V, potential difference. Okay. See, the resistivity is E divided by J, or E equal to J into rho. So, J is current density, and we can write this current density as NeVd. Vd is drift velocity, E is charge of the electron, and N is electron density. Next, we can write from the above relation Vd as E divided by Ne rho. And instead of E, we can write V by L. So, that is V divided by Ne rho into L. So, current density as current per unit area, and E is potential difference per unit length. Next, conductance and conductivity. Conductance is reciprocal of resistivity, and its SI unit is mho or per ohm. Conductance unit is per ohm, and conductivity is the reciprocal of resistivity. Its SI unit is per ohm per meter or mho per meter. And one more important and common unit for conductance is Simon. Per ohm or mho, instead of per ohm or mho, you can use Simon, and conductivity is Simon per meter. Okay. So, next one is temperature dependence of resistances. Temperature dependence of resistances. See, we have already discussed Ohm's law is valid only at constant temperature. As the temperature varies, resistance also varies. See, the resistance of a material is M divided by N E square tau into I by A, or L by A. L by A. See, when the temperature increases, the number of collisions increases, and due to this collision, to more internal energy or relaxation time decreases. So, therefore, resistance increases. So, next term is temperature coefficient of resistance. See, what is this temperature coefficient of resistance means? Fractional change in resistance per degree centigrade is temperature coefficient of resistance. That is, change in resistance upon original resistance per degree centigrade or per unit temperature. Suppose R naught is the resistance at 0 degree centigrade and RT is the resistance at a temperature T degree centigrade, and T is the temperature. So we can write alpha, that is temperature coefficient of resistance, alpha equal to RT minus R naught upon R naught T, or for two different temperatures T1 and T2, corresponding resistance R1 and R2. We can write alpha as R2 minus R1 upon R1 T2 minus R2 T1, where R0 is the resistance at 0 degree centigrade, RT is the resistance at T degree centigrade. Similarly, R1 and R2 are resistances at temperature T1 and T2 degree centigrade respectively. And remember, this alpha is positive for conductors and negative for insulators, semiconductors. Next term, electrical energy and power. See, we have already known that energy is measured in terms of work done, yes, and power is rate of doing work, okay. See, when a conductor of resistance R is connected to a source or cell, an amount of energy dissipated as heat in the conductor during the time interval delta T is current potential difference into delta T. Because how we'll get this expression means we have already known what is potential or potential difference, work done per unit charge or work by charge. So work is charge into potential, and that charge we can write it as current into time, okay. So the energy dissipated per unit time is power dissipated, and we have P equal to work by time, that is I into V, and using Ohm's law we can write V equal to IR, we get P equal to I square into R, or by using V equal to IR we can write I as V divided by R. So I into V is V by R into V, that is V square upon R. Cleared? Okay, so these are the some important relations between potential difference, current, power. If you want to measure the energy means simply power into time measures the energy. Suppose 1 kilowatt is the power used 1 hour, then the energy is 1 kilowatt hour. 1 kilowatt hour is the unit of energy and kilowatt is the unit of power. Clear? Okay. Now, sources of EMF. Already all of you know cell, chemical cell is source of EMF. The electromotive force is the maximum potential difference between two electrodes of the cell when no current is drawn from the cell. It means if the cell is not in use and if you are measuring the potential difference between positive and negative terminal of the cell, and the potential difference itself is the electromotive force of that cell. Comparison of EMF and potential difference. See, EMF is the maximum potential difference between two electrodes of the cell when no current is drawn from the cell. That is, when the circuit is open. And potential difference or terminal potential is the potential difference between any 2 points in a closed circuit. And if you are measuring the potential difference between two electrodes when the cell is in use, then we can say it is terminal potential. Okay. Next, second one is, it is independent of the resistance of the circuit because the cell is not in use or the circuit is open. And the potential difference, it is proportional to the resistance between the given points. If the resistance is more, we are getting more potential difference. Next, the term EMF is used only for the source of EMF, but potential difference, it is measured between any 2 points of the circuit. Means we can measure the potential difference across resistance, across capacitor, across cell, etc. Is it clear? Okay. Next, one more difference. EMF is greater than the potential difference any 2 point or any 2 points in a circuit. And here potential difference is greater than when the cells is being charged. So these are the some differences between EMF and potential difference. And if you are measuring the potential difference across the cell, when the cell is in open circuit, it is EMF. When the circuit is closed, if you are measuring the potential difference between two electrodes, that is the terminal potential. Remember. Is it clear? Okay. So now, by knowing about the EMF and potential difference, okay, let us to discuss the terms internal resistance of a cell. So what is this internal resistance of a cell? The opposition offered by this cell or by the electrolyte of the cell to the flow of electric current through it is called the internal resistance of the cell. Internal resistance of the cell. The factor affecting internal resistance of a cell. Larger the separation between the electrodes of the cell, more the length of the electrolyte through which current has to flow, and consequently a higher value of internal resistance. Greater the conductivity of the electrolyte, lesser the internal resistance of the cell. And internal resistance depends on the nature of the electrolyte. The internal resistance of a cell inversely proportional to the common area of the electrodes dipped in the electrolyte. The internal resistance of a cell depends on the nature of the electrolyte. See, usually that cell is represented by two important factors. One is EMF and another one is internal resistance. So this dotted rectangle, in that dotted rectangle, okay, two parallel lines and one resistance is shown. That one is the symbol of cell. Here small r is the internal resistance and capital E is the EMF. And here red resistance is given, no, that one is the external resistance. If the cell is not connected to the external resistance, and if you are measuring the potential difference across the cell, then it is EMF, and when it is connected, at that time it is terminal potential. So here V is the terminal potential and E is the EMF. See, let us to apply Kirchhoff's rule. So EMF equal to current into resistance plus current into internal resistance. And by taking current is same because small r and capital R in series. So we can write current I equal to E divided by capital R plus small r. This relation is called circuit equation. And one more important point, the maximum current that can be drawn from a cell for R equal to 0, that is short circuit. For short circuit, current drawn from the cell is maximum, and it is E divided by small r. Next one, we go to combination of cells. Combination of cells has two types of combinations, series and parallel combinations. So that can be discussed in next class. Okay, thank you.